Вот. Давайте я начну по-русски, да? А если будет надо, то мы переключимся на английский. Значит, что было в прошлый раз? Я в прошлый раз сформулировала, что такое веер, но мы этим по большому счету не пользовались. Сегодня я хотела начать немножко про нормальность поговорить, а потом уже говорить про то, как и зачем нам нужны вееры. Во-первых, определение стандартное. Мы говорим, что А целозамкнуто в своем поле частных, целозамкнуто в своем поле частных. Если вдруг так вышло, что мы взяли какую-то дробь, удовлетворяющую уравнение целой зависимости, она сама лежит в А. То есть любое f из такое f, для которого есть уравнение fn плюс a1 fn плюс 1 плюс an нулю, значит, что на самом деле f была из А. Иногда мы будем для краткости говорить, что такое А нормально. Вот. В таком случае, на самом деле, это означает, что соответствующее многообразие это будет нормальное афинное алгебраическое многообразие. Ну, в целом, почти все многообразия, которые люди рассматривают, такие, потому что с ними гораздо удобнее работать. Ну, то есть, сейчас, что мы хотим? Мы, в принципе, это у нас будет определение. Многообразие x называется нормальным, если алгебра функции на нем вот такая вот. И давайте какой-то пример. Самый такой стандартный. Самый стандартный пример. Ненормального многообразия. Это вот такой вот клювик. Как его только правильно нарисовать? Правильно я нарисовала или неправильно? X квадрат равно y куб. Ну, либо так, либо вот так. Я сейчас не могу сообразить. Вот. Значит, почему вот это свойство не выполняется? Какая у нас есть функция? Давайте я это явно напишу. Поделим это равенство на y квадрат. Получим, что x делить на y в квадрате. Это будет y. Вообще, какие функции на этом многообразии есть? Это будет как бы c от x, y, фактор по идеалу рожденному x квадрат минус y куб. Ну, понятно, что это элемент из фраг этой алгебры, уравнение целой зависимости, и мы можем понять из соображений градуировки, что на самом деле x делить на y здесь не лежит. Там мы можем вес x назначить 3, y 2, и такой штуки веса 1 у нас вообще не будет в этой алгебре. Вот. Вот здесь он не лежит. Хорошо. какие-то примеры, которые точно нормальные. Hello. So we just started talking about normal varieties. So here I just gave the definition of what is a normal variety.
Yes, but I know it.
Окей. Ладно, дальше по-английски. Если есть вопросы, вы задавайте, чтобы все поняли. Each smooth variety is normal. And it is very important that if X is irreducible and normal, then its singularities are not very bad. So its codimension is at least 2. It is just a basic factor, just as a motivation why normal is so important. Now, what does it mean for us and what do we want? I want to define the criterion for a toric variety to be normal. So in our definition, we had some sets. If we take a set A, which is some characters M1, M2, etc., MS, do you recall that we have constructed chi power M1, chi power M2, etc., 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 and then we took its algebraic closure. So in this construction, the variety will be normal if and only if this set satisfies the following property. We say that this set is saturated if and only if the following equality is held. The semigroup generated by these points will be equal to the following intersection. If we intersect the lattice generated by these points intersected with the cone. So I'm going to prove the following criterion. Our variety, the corresponding toric variety, is normal if and only if A is saturated. X is the closure of the image of that phi A. Okay. 1. So, should I give some examples? The very simple example when this is not true, it is for this case. If we take M equal to one-dimensional lattice, and we take M1 equal to 2, M2 equal to 3, we have 1 which is, so what is our semigroup? 0, 2, 3, and so on. So in the right hand side, we will have all the integer points, but in the left-hand side we will not have 1. 1 is only on the right-hand side. And this variety is not normal. And clearly, we always have this inclusion. And now I want to prove this criterion in both directions. Okay? Maybe first I will say as an example without proof. That any unique factorization domain is integrally closed in its field of fractions. It is not very difficult. We will check it. And as a consequence of this fact is that Laurent polynomials and variables, they are also integrally closed in its field of fractions. I will need it for the proof, so I state it right now. So this was as a prerequisite for the proof. Now the criterion. In one direction, suppose that if the set is not saturated, clearly we can construct an element from the field of fractions which satisfies the good equation. So if A is not saturated, we can take a point which is in the right-hand side. What is the right-hand side? It is this intersection. So each m from this set, it corresponds to a rational function. So let m be in the set. So chi m is this set, and we know that it is in the cone, so there is some common denominator. If we multiply m by this denominator, it will be in the lattice. So there exists some q such that chi m power q will be in A itself. So this is chi m power q equals some other element of A. It is the equation with the highest coefficient equal to 1. And we conclude that if the variety is normal, then chi m should belong to A, and then m will belong to the semigroup generated by these vectors. It was the easy direction. So if this property is not held, we found an element which contributes the normality. And now the difficult direction. How can we prove it? Suppose that we have f from this field of fractions. Then suppose that it satisfies the equation f power n plus a1 fn minus 1 plus. So it satisfies some equation. I want to prove that in fact f belongs to this algebra itself. Okay. First of all, we can say that this is an equality in Laurent polynomials. All this stuff is some Laurent polynomials. We know that Laurent polynomials are integrally closed in its field of fractions. So we obtain that f itself is a Laurent polynomial. Maybe its monomials have nothing to do with our semigroup. We don't know. But f is a Laurent polynomial. And if we write down its expansion, if we write it down here, and if we open all the brackets, everything will vanish. Okay. What now? Let us... I want to take the cone. I want to take the cone generated by our monomials. Without loss of generality, it is a full dimension. If not, it is not very hard to modify the proof. First, we assume dimension. We can take any facet and hyperplane passing through this facet. So let H be a hyperplane.
Еще раз, facet это что по-русски?
Гипергрань. Ну, в смысле, мне в целом все равно. Могу просто взять любую плоскость, которая ограничивает конус.
Да, я просто перевод забыл.
Да. In fact, no need to be a facet, but just any hyperplane which is sign positive on our cone. What about the monomials of f? So suppose this is our cone, this is our hyperplane, and we know that f is a Laurent polynomial. We can mark its monomial in the picture. So if f is everywhere, if some monomials of f are here and some are there, this will be a contradiction. Show that all the monomials of f are in positive half space. I will not write down this proof, but I will explain it. Okay? So for each monomial of any of f and any of ai, I can take its distance from this plane. So this distance is positive, and this distance is negative. And if we expand all the brackets, then the distances, they sum up. For example, if I have some monomial here, if I take its mth power, the distance will be multiplied by m. If I multiply several monomials, which is 3, a1, no, not a1, alpha 1 plus, if I multiply two monomials, the distances will sum up. If I multiply several monomials here and multiply by some coefficient, then we will also add the distance from this coefficient. I didn't write down, but all the coefficients there were taken from this. So for them, this distance will be positive. Okay? And let us take the most negative terms with respect to this distance in this expansion. They will come from the most negative terms of f. If there is one term, it is easy. It will be only its mth power, and it will not vanish with anything. And if there are several ones, then they will form a polygon. And we take any its vertex, its nth power will not vanish with anything. Okay? It will be at the most far plane, and it will be extremal. No other terms will have the same power of variables. What did we obtain? We obtained that all the monomials of f are in H+. If this cone is not of full dimension, we can easily modify the proof, because first of all the monomials of f will be in the same subspace, using the same reasoning with the distance. And then we will restrict inequalities in this subspace. And so any cone can be bounded by such hyperplanes. It is just we can take the generators of the dual cone. And now we have shown that all the monomials of f are in this cone. Okay? Do you believe me? Еще раз, я вот сейчас вроде как доказала, что все мономы f на самом деле лежат в конусе, натянутом на мои исходные m-ки. Потому что для любой плоскости, которая ограничивает этот конус, они должны оказаться в положительном полупространстве. Иначе у нас будет беда с уравнением целой зависимости. Хорошо.
Ну, совсем понятно, что за беда. Можно еще?
Да. Мой план такой. Вот это вообще некое уравнение на полином Лорана. И, как полином Лорана, там есть какие-то иксы в количестве, размерность нашей решетки m, с которой мы там всю дорогу работаем, да? И когда мы туда подставим, все скобки раскроем, все должно умереть. Все все мономы Лорана должны сократиться. Я утверждаю, что я могу найти какой-то сильно крайний, который ни с кем не сократится.
смысле, который дает,
Да.
если он отрицательный, то самый отрицательный.
Да. Ну, то есть я беру какую-то плоскость, ограничивающую конус, такую, что все мономы конуса будут в одной стороне. То есть они все в этой штуке будут давать расстояние от плоскости в плюсик. Вот, я говорю, у F все мономы тоже в положительной части лежат. Почему? Если какому-то моному не повезло, он оказался в отрицательной части, я беру самый, значит, отрицательный моном. По расстоянию смотрю, просто расстояние от этой плоскости. Самый нижний. Вот, как бы, если там на плоскости, да, вот это вот наша H.
И он не сократится из-за того, что вот именно первый член это F степени.
Да, именно поэтому не сократится, потому что все остальные члены, они не могут его сдвигать в отрицательную часть, они могут его только в положительную подвинуть. То есть вот был моном, да, у него есть квадрат и куб, да, куб будет где-то здесь сидеть, вот здесь вот. Вот здесь будет сидеть куб, а квадрат будет сидеть здесь, он с ним не сократится, и еще может быть подвинутый вверх. Что ж такое? Так, поэтому еще раз, для любой h, которая ограничивает наш конус, все мономы f лежат в положительном полупространстве. Вот, хорошо. Okay, this was the first step of the proof. I explained why all the monomials of f are in this cone. Now I want to state that they are in fact in the lattice generated by M1, etc., Ms. So, recall that F was taken from the field of fractions of this stuff. So F is a Laurent polynomial. So F is some what is our notation? By the product of some characters. Oh, they were.
So even now we have to show that the coefficients are coming from Z.
Sorry?
The next step is that the coefficients are coming from, the coefficients are integers.
No, not quite. One moment. That was chi and 1, etc. Chi ms. Okay? I come back. I want the powers which enter in F belong to this lattice. This is what I want to explain now. They will be in the cone, they will be in the lattice.
Hence they will be in.
Yes, hence they will be in the semi-group generated by these vectors, and F will belong not only to Frag, but to this algebra itself. Okay? But this is much easier. So this is something divided by something. Okay? We can multiply it by the denominator. F, which is a Laurent polynomial, times some Laurent polynomial where all the power is a linear combination of mi. This is a combination of M1, etc., MS. This belongs here, okay? And then because the other sum where this also belongs to the semigroup. Now, let us fix any lexicographic, for example, order and take the highest term of F. It will multiply with something here, and we will obtain something from here. So the highest monomial of F will be the fraction of some monomials divided by some other monomials. So it will be in the lattice. The highest term of f will belong to z and 1. Maybe it is a little bit vague. I can explain in Russian if you need. Понятно, что произошло? Сергей? Понятно? Хорошо. Понятно? Ладно, все, тогда окей. Okay, then I can subtract the highest term of f and continue the same explanation. I will obtain that all powers which enter in f in fact belong to the lattice generated by m1 etc. ms. Then I use the normality. All the monomials which are in f in fact belong to this algebra without frac. And f is in our algebra. So it is integrally closed in its field of fractions, and the corresponding variety is normal. Yeah, done. We have proved the criterion. So what is the profit if we want to work with defined toric varieties which are normal? It is enough to use only the cones, to restrict ourselves to the cones. So, no. Fine. Toric varieties. Come from cones. So what was our construction for the cones? We said that we have a lattice M, we have a cone sigma check, we take a sigma check intersected with M, and we took this as an algebra of functions. So this was our affine variety constructed by a cone. And on the other hand, we've had the construction which takes M1, etc., MS. So in fact, in this case, we said at the very first lecture that it was an affine toric variety such that its torus has the character lattice Z M1, etc., MS. It was in the very first lecture. For example, if we took vectors 1, 1 and 1 minus 1, we didn't get the whole torus. We got only the subtorus which is inside. So in this case, we take the cone generated by M1, etc., MS, and obtain the very similar construction. So maybe I should explain it a little bit more. If I'm at this side, okay, we have the Gordon lemma. Should I prove it or not? The Gordon lemma says that this semigroup is finitely generated. Did I prove it? Было это или не было? Кому-то надо доказывать, что вот эта вот полугруппа конечно порождена. Только честно. Было это где-то у вас или не было? Ну, доказать надо, да? Или не надо? Кому очевидно, кроме Максима? Okay, then I will prove it. I will prove that this semigroup is finitely generated. Okay, sigma check is generated by some vectors. Okay, these are the generators of sigma check, and then I can take the figure which is I need to know them. Okay, let them be also M1, M2, etc. MK, A1, M1 plus AK, MK, where the coefficients are from 0 to 1. Okay? This is a bounded figure. I can intersect this figure with M. I said that this will be our finite set of generators. So we have included all the vectors here because they're combinations with only one AI equal to 1. So we have all our generators. And now if we take any other point which is here, how can we write it down? It will be some BI MI, where BI are greater or equal than 0. We can say that each BI is its integer part and its fractional part. Okay? And so this is this can be expanded using MI, which were at the very beginning, which were the generators of the cone. And the remaining part is in our figure, and it is in M because we have subtracted some element from M from some other element of M. So by construction, it is in this finite set of generators. And we are done. So this stuff is finitely generated. What else should I explain? Yes, so if I have this construction, I fix some finite number of monomials which will give us the same construction. And on the other hand, if I have a finite number of vectors, then I generate a lattice by them, and I generate a cone. Clearly, any integer sum from the cone will be a function, will be a regular function on our variety. And it will be the same. So all the integer points from some cone. So in fact, these two constructions are equivalent if we want our varieties to be normal. Okay. This is what I wanted to say about affine toric varieties. And now we can glue up abstract toric varieties. Okay? Any questions at this point?
Can you repeat the last part? We have we know how to construct affine toric varieties from a given cone by the help of this affine semigroup. Now you say that this is equivalent to the construction when
Yes.
we start from a normal toric variety.
Yes. I mean, if I have a normal toric variety in the sense of a finite number of M1, M2, etc., Ms, I assume the set M1, etc., Ms to be saturated. Yes. So, this is my semigroup. Just this is my construction. I take this semigroup. I know that this set is saturated because, and hence, this intersection will be equal to. It will be equal to the semigroup generated by them. Okay. And now I take all the, so this is my lattice. I don't work with all the integer points, but I work with this set. And I say that in fact we have this construction which is performed for m equal to this lattice and the cone sigma check equal to this cone. So in this construction we replace everything with the objects we have and we obtain absolutely the same Toric variety because it will have absolutely the same set of generators. Okay. So now we have our aim for today is Toric varieties from fans. What is a fan? It is a finite set of cones with some properties. It is a set of cones finite. Such that first of all, if tau is a phase of sigma, if sigma is in our fan and tau is a phase of sigma, then tau is also in our fan. And then if sigma and sigma prime are in our fan, then tau, which is the intersection of them, is also in sigma and is a phase of each. So I've mentioned this definition last time, but it is very, very important, so I want to repeat it. What examples can we give? First of all, any cone is itself a fan. So this cone, if we take it with all its faces, so the two-dimensional cone, 2 rays and 1 point. Maybe I draw this one. If I draw 3 cones which cover the whole plane. We have 3 cones of full dimension, 3 rays and 1 point. Maybe.
В прошлый раз было pointed cones.
Thank you very much. Pointed cones. Pointed. Yes. Yes. Да. Острые конусы, мы не хотим проблем. Сейчас. Maybe I draw one nice cone, nice fan and one strange fan. So a nice cone is, let us take split this octant into 2 parts. Okay. This satisfies the condition. And now maybe I will draw one exotic fan. I can throw out the cones of full dimension. I will have only 1 point and 3 rays. This is also a fan. And for example, this condition is held if we take 2 elements of our fan. Their intersection is the 0 point, and it is the face of each of them. Now what do we want? We have no check here, and we've had check at the previous slide. Let us say what happens. Suppose that we have a fan. So we
How
fix.
is not going to ensure every cone is pointed?
Sorry?
You do not pointed cone, so we are now going to assume that every cone in the fan is pointed.
Yes, I forgot to say, today I forgot to say, but the students corrected me. Yes, in this construction I want all the cones to be pointed. This is necessary because right now I'm going to pass to dual cones. If my cone is not pointed, then sigma check is not a full dimension. And I will not get what I want. I want to get an affine toric variety which contains a torus of full dimension. And this will not be true. Okay. We fix sigma, and for each cone in our fan, construct what we've done before, the spectrum of sigma check intersected with M. We fix sigma in MQ. Okay? So, as before, we have a lattice M, we have its dual lattice N, and all the cones without check live in NQ. All the cones with check live in MQ. Okay? We say that let U sigma be this affine toric variety. And now we want to glue them up. How do we do this? First of all, if tau is the phase of sigma, then tau is sigma intersected with some U orthogonal, and U tau is given in U sigma by chi U is non-zero. So U tau will be a principal open subset in U sigma, first of all. And then if we take, we have sigma and sigma prime such that tau is their common phase, then we will have U tau, which is in both of them, and we will identify them. I think we will check it in the seminar. Do you want an example or some explanation? An example. Okay. Maybe the very first example will be in dimension 1. Let us first construct P1, and then we will construct P2. Okay? What is about P1? It has dimension 1, so this is its fan in 1 dimension. Okay? We have, for example, U1 and U0. And U1 corresponds to this. This is its algebra of functions. These are polynomials in 1 variable. Okay? And what is U0? U0 is this ray, and its algebra of functions is polynomials in x power minus 1. Now, what about the intersection for this point? What is our construction? This is the cone, then its dual will be the whole plane. It will be the Laurent polynomials in one variable. This is the intersection. U0 intersected with U1. And what happens in U1? It is an affine line. So if the coordinate is not equal to 0, we take its inverse and we go to the other chart. So these two charts are glued up by a set where the both variables are not 0. And then one is the inverse of the other one. So this is the standard construction of P1. Okay? Нормально или не очень верится? Хорошо.
Ну, то есть формально мы что-то по идеалу берем, да?
Мы клеим из карт. Какой предел вы хотите брать?
Какой предел?
Я не разбираюсь в каких пределах. Я просто знаю, что если мы клеим из карт, как бы мы можем... Вот сейчас, единственный момент, который плохой, это в отделимости. Все остальное согласуется. Да. So this was the example for P1. Maybe I want to draw the example for P2. This is our fan. Maybe this will be U0, U1, and U2. U2. How do we construct U0? It will be the spectrum, the dual for this curve will be the same curve. So it will be a spectrum of x, y. U1, it is sigma, so it is sigma. Now what is sigma check? Sigma check, it will be orthogonal to this one and orthogonal to this one. Okay? This is sigma check. So U1 is the spectrum. It is itself isomorphic to the affine plane, because this cone is generated by two vectors with the determinant equal to 1, minus 1, and minus 1 to 1. Or x power minus 1, x power minus 1, y. Okay? And in the same way, U2, so this is sigma. Sigma check is this one. So it is generated by y minus 1, x, y minus 1. And what are the intersections of the charts? If we take U0 intersected with U1, this is the Toric variety which corresponds to this cone. It is sigma. Then sigma dual is this one. And I hope you understand that it is C star along the first coordinate and C along the second coordinate. It means that x is not 0, and if x is not 0, how can we pass from this one to this one? You take the inverse of this coordinate, and you can express this using these two coordinates. It is the same as we glue up P2 in the usual way from 3 charts. Don't you believe me? Okay, then I can write it down more precisely. What is the projective plane? I didn't use Z. Z0 times Z1 times Z2, okay? So if Z0 is non-zero, this is my U0. X equals to Z1 over Z0, and Y equals Z2 over Z0. Okay? Okay? Now, what about U1? U1 is Z1 is not 1. Now we have coordinates Z0 over Z1, and we have Z2 over Z1. But we know that this is X, so this is X minus 1. And we know that this in fact equals to 2 over Z0. If Z0 is non-zero, then it is equal to this stuff. And we can rewrite it as Y, this is Y, times X power minus 1. Okay? It coincides with what I have stated here. And if we take intersection with U2, it will work in absolutely the same way. So it will be the honest P2. Okay. I think the last picture will be discussed at the seminar. I think we will discuss this picture at the seminar. And for this picture, it is in fact very similar to P2, but we just throw out some points. So we don't have the internal part. Maybe I should say about torus orbits right now. The cones encode the torus orbits. So how does what is the dimension of P2? Yes. So we want to act with torus of dimension 2. It is just not for the construction, but it is some, как бы по-английски, лирическое отступление. Короче, это лирическое отступление про то, что будет потом. Да. So it is not the material of this lecture. This will be later, but I think it is very important, and I can show it right now. So what are the torus orbits? How does the torus act here? So we point the element of the torus T1, T2. It maps Z0, Z1, Z2. It is mapped. Without loss of generality, I can write it in this way. T1, Z1, and T2, Z2. T1, Z1, T2, Z2. Okay? These are homogeneous coordinates. What are the orbits? First of all, in our P2, we have the locus where all these zi are not zero. I state that they all can be moved one to the other. So there is an open T orbit. T orbit. Z0 is not zero. Z1 is not zero, and Z2 is not zero. Why is it an orbit? We can make, for example, for any 2 points, we can make Z0 equal, just taking another homogeneous coordinates. And then we find T1 and T2. And due to our conditions, they will be all non-zero. Okay. Then, what about the other points? There are 3 points which are fixed under this section. So the point 1, 0, 0, it is a fixed point of this section. Why? Just because we multiply these coordinates and they do not change. I stated that all the similar points are also fixed under this section. Because when we take homogeneous coordinates, it is the same as 0, T1, 0. So we have 3 fixed points. And so these are 3 fixed points. Okay? And now we have 3 orbits of dimension 1. They correspond to one homogeneous coordinate equal to 0, and 2 others are non-zero. It is very similar if we act only on P1, and we say that so I didn't mention it here, but at this picture we have also the action of one-dimensional torus. And also this is the open orbit, and these are 2 fixed points of the section. And now if we are in P2 but one homogeneous coordinate equals to 0, then in fact it is a copy of P1 which lives inside, and in it we have an open orbit and we have 2 fixed points. Okay. What else? I wanted to say what is the toric variety if we just take one-dimensional cones. I state that this is P2 without these 3 points. Without 1, 0, 0, 0, 1, 0, and 0, 0, 1. This is this variety. It is not very good. It doesn't contain its limit points, but it exists. It is a toric variety. Okay. This was about the examples, and now I want to explain a little bit why the result is separated when we glue up all these charts. Okay. We were very close to it when we had some equalities with cones. So, what about I state without proof that it suffices to show that U tau in U sigma times U sigma prime is a closed embedding. if you want to discuss this, let us do it at the seminar. So when we glue up, everything agrees well, but the only problem is why do we get a separated algebraic variety? I stated for the separation property this is enough, and if it is a closed embedding, it is equivalent. These are affine algebraic varieties. So it is separated here and it is separated here. When we have map on this side at the algebra functions, we have map on the other side. So this is a map. I'll write it this way. The tensor product, it is mapped to the algebra functions on U tau. Okay? And the fact that it is a closed embedding, it is equivalent to the fact that this map is surjective. This is a basic fact from algebraic geometry, from final algebraic geometry. Okay, and now we come to the combinatorial meaning of this fact. So we know what are these algebras. It was at the previous lecture. It was in fact S tau. S tau, which is tau check intersecting with M. Okay? And it was a sigma. And this was a sigma prime. Okay? And we want this map to be surjective. We've had many different properties for all this stuff. But do you remember we had the separation property? It was exactly this case. If we have some sigma and this is sigma prime, and this is tau. We proved last time that there is always an element U. It is positive on sigma and negative on sigma prime, such that tau equals U orthogonal, and U orthogonal is equal to sigma prime. Okay? It was done last time. Now we want to get profit of it. So I want this map to be surjective. Also, maybe 2 lectures ago, we have proved that S tau is in fact S sigma and one more generator. And we take minus U. Okay? What does it mean? It means that if we take any element from here, we can decompose it as an element from sigma and some power of minus U, but minus U belongs to sigma prime check. So in fact, this map is surjective. Okay? Should I write something more? I mean, we have a map here. If we take a tensor product of these two algebras, if I take two monomials and if I multiply them, then I sum up the object with which is at the power. So in fact, I have S sigma plus S sigma prime maps to S tau. I check whether it is surjective. So to show that it's surjective, I say that, in fact, if I find such an element U, and U belongs to M. So by this construction, it belongs to M Q, but we can take its integer power, and it will belong to M. So without loss of generality, I may assume that U belongs to M. So this is some character. It corresponds to some character. And now this equality shows that chi power minus U, it will be a rational function from S sigma prime. It will be a rational function from here. And so we take that product and we obtain any element from this algebra that we need. Okay. And so when we glue up a toric variety from charts, the fact that it is separated, it follows from the separation property for cones. I have more or less explained this. If you want it in more details, then we will discuss it in the seminar. Any questions? I think I'd like to stop here, but if you want, I can explain anything we've done. Any questions? Okay, and also I planned to give you sheet 1 today. It is only in Russian, and sheet 1, it has some deadline. I wrote the 5th of March. If it will be hard by some reasons, you can write me in Telegram. But generally, try to do it at time, because there will be many other sheets. And at the moment, we have one assistant. У нас сейчас пока только один ассистент, к сожалению, это будет Марк Черебетов. Вот, то есть решайте, сдавайте. Сейчас я напечатала одну штуку, я сейчас попробую послать, если у меня поймается интернет. И семинар на сегодня. Семинар по-английски, а листочек по-русски. So the sheet is in Russian. I'm very sorry. If you want, there's the previous version in English. It is Varieties tablets. This is the seminar for today. Very basic.
You will be sending this to the group as well, right?
Yes. I mean, more or less, this is the sheet from 2 years ago. 3 years ago, there was a discussion in Russian version. I eliminated 2 problems. I added 2 new problems. But it had not time to make it the appropriate way in Russian. Так, если вы хотите отпечатать, вы пишите.
I will look at it and let you know if I need.
Опа-па.
Отпечатал где-то? Если отпечатал, вы говорите. Семинар дело такое, более добровольное. Если вы все поняли про семинар, то просто не ходите.
А у кого листочек именно будет пробовать?
Семинар?
Не семинар.
Листочек сейчас опрошено. Сейчас мне не сопротивляю, его тоже не печатать. Ну не, на самом деле, как бы, сейчас будет пачка отпечаток, если будет, тогда отпечатать.
Правильно является промышленным. Вот тогда используется свои задачи. Понимаете?
Тогда возьмем
Ну, ты типа,
Ты на торическую геометрию пришел.
ты пришел на торическую геометрию?
Нет, я не был.
А, окей, классно. Что же теперь? Здрасте. Я вышел, меня тут.
Thank you.